Hello everyone, Namaste. I am Dr. Rakesh working as a ANRF-NPDF under the guidance of Professor Pradeep C. Parameshwaran at School of Chemical Sciences, IIT Mandi. First of all, I would like to thank ANRF-IIT Mandi for giving this opportunity. Here is my ongoing research topic on bioinspired construction of synergistic polyoxometalate LDH interface-derived microreactor heterojunctions as efficient water-splitting electrocatalysts. Let me introduce why water splitting has become a more important area. As we know, there is a lot of increasing global energy demand, which is expected to be 46 trillion watts by 2100. And the large consumption of fossil fuels also led to rising greenhouse gas emissions and climate changes. Although we have abundant renewable energy in the form of solar, wind, hydro, by using this renewable electricity to split water through electrolysis, which can produce the hydrogen evolution at a cathode, oxygen evolution at anode. By storing these energies further, it can utilize in a potential applications. Among the HR and OER is a kinetically sluggish reactions which need 4 electron slow process, and in order to reduce their energy barrier and accelerate further, we need to develop a efficient electrocatalyst. As we discussed, renewable electricity can produce hydrogen, which is a clean fuel having high energy density and without any carbon emissions, which could be a key pillar for the future clean energy economy and sustainable energy future. In this regard, there is a lot of hydrogen demand is going on in the upcoming years in the different fields. Recognizing this, India has established National Green Hydrogen Mission, which aims to become a global hub in green hydrogen and exports, which is supported by Ministry of New and Renewable Energy. Among the different hydrogen production technologies, electrocatalytic water splitting has become a significant which produces high purity green hydrogen without any carbon emissions, operate under mild conditions, which is also scalable and sustainable process. To meet this hydrogen demand, we need efficient electrocatalysts which should possess certain parameters like low over potential and low top fill slope and paratic efficiency, high electrochemical surface area. Moreover, they should be effective over a wide range of pH. Although significant advances has been made so far, however, there is still challenges remains in terms of using expensive noble metal catalysts like iridium, ruthenium, platinum, and high over potentials, and interface engineering is not up to the optimum level. Poor conductivity and HR, OER kinetics are slower, and poor stability of the materials. In order to overcome this, developing stable, conductive, high surface area, corrosion resistant materials, noble metal free catalysts are essential. Moreover, engineering eco-friendly strong heterointerfaces for overall bifunctional HROR under mild conditions is required. In this regard, in our work, we have chosen the polyoxometalates and layer double hydroxide materials as two complementary materials, where polyoxometalates are metal oxide clusters well known for their rich redox properties and tunable composition and catalytic activity. However, they have poor electrical conductivity, high solubility in polar solvents, and limited stability and low surface area. In contrast, LDHs are low cost and earth abundant materials and excellent wear activity, abundant active sites, high surface area. However, they have certain limitations like poor conductivity and instability in nature and restacking behavior in the solution. Therefore, integrating pumps with LDH, we aim to combine the advantages of both materials by minimizing their limitations. However, simply mixing up pumps with LDH is not sufficient way to produce the strong hetero interfaces. The interface must be controlled in a suitable manner. By constructing the hetero interface between these two materials, further can facilitate efficient charge transfer, more active sites, and improve stability for enhanced HROR activity. In order to establish such type of a heterointerface in a suitable matrices, we have inspired from the bioinspired assembly strategy by natural biomineralization process found found in the diatom cell wall formation, where polyamides are responsible for the silica deposition and nanopatterning of their cells. The polyamides within the presence of certain multivalent anions can dictate the final morphology of the silica under neutral pH conditions in aqueous medium. By inspiring from this by-inspired research concept, we have established research objectives as follows to develop. We have to develop a stable, noble metal-free three-dimensional microreactors using a bioinspired assembly strategy in which we have to establish a strong hetero interface between POM and LEHS, which is further generate the crystalline derivatives under controlled thermal treatment. Further evaluate their overall water splitting and stability and durability. In this regard, in the first attempt, we have successfully synthesized the single layer LDH and from the bulk LDH under exfoliation method and well characterized by SEM-TEM analysis, and Exardic confirms their crystallinity and Tyndall effect showing for their colloidal behavior. In the latter stage, we have developed a bioinspired assembly process where we have assembled LDH and POMs in the microreactor structures by electrostatical method and confirmed by the SEM-TEM analysis. Further, the structural analysis confirmed by FTIR Spectra XPS confirmed that intact POM and LH components assembled in the microreactors, and initial electrocatalytic results confirmed that the materials are found to be active for both HER and OER. Further optimization is in progress to achieve efficient electrolytic performance. With this, I concluding that we have developed a bio-inspired three-dimensional microreactors and where we have established a strong hetero-interface between POM and LEHS, and which are suitable for the electrocatalytic evolution of overall water splitting, which is underway, and optimization of further this composition and assembly condition is ongoing to improve electrocatalytic efficiency. Overall, this work will contribute efficient, low cost and sustainable solutions for clean energy future. Finally, I sincerely acknowledging ANRF for financial support, Director, School of Chemical Sciences, and SRIC IIT Mandi for institutional support, my mentor, Professor Pradeep, and group members. Thank you. Jai Hind.